We all know we have two types of semiconductors, extrinsic semiconductor and the other is intrinsic semiconductor. If we plot a graph of conductivity with temperature for intrinsic semiconductor, then the graph is quite simple as the conductivity of intrinsic semiconductor increases with temperature. However, if we plot the relation of conductivity with temperature for extrinsic semiconductor, it is not as simple. Initially, at low temperature, since there is very less energy available for random motion of charge carriers, the conductivity of semiconductor increases, however, up to only certain temperature. This temperature is near to room temperature. But if the temperature is increased further, then the conductivity begins to fall up to a certain temperature, and the temperature at which we get the minimum conductivity of the extrinsic semiconductor is referred as Curie temperature, which is represented by Tc. When the temperature is increased after the room temperature, majority carrier concentration will remain almost independent of temperature, and minority carrier concentration increases with temperature. Mobility of charge carriers decreases, hence the conductivity of extrinsic semiconductor will be decreasing with the temperature. At Curie temperature, minority carrier concentration approximately equal to majority carrier concentration, and an extrinsic semiconductor will become intrinsic semiconductor and its conductivity will become minimum. After the Curie temperature, the extrinsic semiconductor will begin to act like an intrinsic semiconductor. Everyone know that for conductors, we have formula for resistance to be equal to R naught multiplied by 1 plus alpha into delta T, where R is the resistance at temperature T, R naught is resistance at 0 Kelvin, delta T is change in temperature, but since we have taken R naught to be at 0 Kelvin, change in temperature will be equal to T minus 0, which is the temperature in Kelvin itself, and alpha is the coefficient of resistance. For conductors, you might already know that the coefficient of resistance alpha is positive, meaning that as the temperature increases, resistance also increases. Since length and area of a conductor does not change, therefore it means that resistivity of the conductor increases, and also you know conductivity is reciprocal of resistivity, therefore conductivity decreases. But you can see clearly from the graph of intrinsic semiconductor that as the temperature increases, conductivity increases, meaning that an intrinsic semiconductor has negative coefficient of resistance alpha, and for extrinsic semiconductors, coefficient of resistance varies with temperature. However, if we talk about normal temperature, which is from room temperature up to Curie temperature, then you can see that when the temperature is increased, conductivity decreases. Therefore, for normal room temperature, extrinsic semiconductors has positive coefficient of resistance alpha. You might think that why we take normal temperature to be from room temperature up to Curie temperature. See, if you are an engineer, then obviously you have to design a semiconductor device which will work in the real life. No one is going to ask you to design a semiconductor device which works well on the surface of the sun. As even if you design one, then there is no one who can validate it. So, when we talk about normal temperature, then we talk about the temperature at which we will be using those devices which you have constructed from the semiconductor. Generally, the room temperature is about 300 Kelvin, And we talk about a little more temperature than the room temperature because when you operate any device for a long time, it gets heated. So it is also important what parameters will be changing as the temperature of the semiconductor which you have designed has increased.